Thank you for joining us. This is Dan Quigley with DSI, and this is episode 23 in our Gleeble webinar series. I want to thank those of you who have been with us for many weeks, as well as welcome those of you that are joining us for the first time. If you missed any of our past sessions, you can find links to videos of these webinars on our website. As always, we hope you find these presentations valuable. Our goal will be to keep this webinar to 1 hour or less. If time allows, we will have Q&A at the end of the presentation. If you have questions, please submit them using the chat feature here in the webinar. We have a lot of people registered for today's webinar, so we probably won't have time to address every question. However, if needed, we can connect you with the presenters for an offline discussion. As I mentioned, videos of this presentation will be available online soon. You'll be able to find a link to this video as well as videos of past webinars by going to our website, which is gleeble.com, and clicking on the resources link in the top navigation bar. Then click on webinars, and there you can view past webinars and sign up for future webinars. And I'm happy to announce that next week's session will be presented by the legendary Dr. Evgeny or Gene Polyak. Dr. Polyak will focus on how Gleeble simulations support industrial steel manufacturing processes. So I encourage you to sign up for next week's webinar on our website. But today we're going to mix it up a little bit. We have 3 different presenters. They're going to share their work. It's my pleasure to welcome the team from Luleå University of Technology, led by Dr. Farid Akhtar and joined by Rosa Maria Pineda and Farnoosh Forazan. The theme of their presentation is the contribution of Gleeble experiments to designing materials from room temperature to high temperature applications. A Gleeble 3800 was installed at the National Thermo-Mechanical and Tribology infrastructure at Luleå University of Technology in late 2016. Since then, the team has been quite busy. They've been very productive and have been generating impressive research. During today's webinar, the team will introduce the research activities at the university and how the Gleeble is enhancing understanding of the microstructure-to-property relationship for manufacturing applications for steels and high entropy alloys. They've also studied continuous casting, stamping, welding, additive manufacturing, and sintering processes. So I want to thank Dr. Akhtar and his team for preparing these presentations and for taking the time to share their work with us. Dr. Akhtar, I'll hand this over to you.
Thank you very much for the introduction. And as you introduced, we will talk today on the designing of materials from room temperature to high temperature applications and how Gleeble contributed in these studies. And we will be 3 presenters. So first I will present, and then Rosa Maria and Farnoosh will present at the end. So we are at the Division of Material Science at Luleå University of Technology. And this is our campus where we are located in Luleå. So Luleå is in the north of Sweden, and we are located very close to Polar Circle. It's a nice place to visit as well. So in university, we are working at Department of Engineering Sciences and Mathematics, where we have several divisions, and in total we are 300 employees. We have 20 research subjects and 7 centers of excellence. And we are located in Division of Material Science. And at Engineering Materials, in Division of Material Science, we research a lot on steels, titanium alloys, stainless steels, polymers, ceramics, intermetallics, and high entropy alloys. We work very closely with the industries and research institutes, so the research can be implemented in applications. So this is an overview of the research at our subject. So our approach is that we want to identify the ways to enhance the properties. We design and tailor the microstructure, mesostructure, nanostructure, and also we tailor the local atomic arrangements to enhance the properties. We develop infrastructures and also develop new and novel characterization methods. So the areas where we are strong in research are additive manufacturing, steels, ceramics, porous ceramics, metal, intermetallic matrix composites, And the new areas that we are exploring more and more are high entropy materials, 3D printer of different materials, lightweight alloys, intermetallics, steels, surface design of materials, and shaping of materials for optimum design. If we look at our group, we are 4 seniors in the group. We have 2 research engineers. We have 5 postdoctoral researchers, 11 PhD students, and roughly around we have 12 master students working on their thesis in engineering materials. So as you said that we had developed the TMTEST infrastructure, that is a thermo-mechanical and tribological infrastructure. The idea was to establish infrastructure where we can determine the properties of the materials and design materials for high temperature applications and materials for harsh environments applications. So for today, we have this structure for our seminar. So first I will talk about microstructure tailored stainless steels with high mechanical performance at room temperature, intermediate and elevated temperature. And after me, Rusa Maria will present study of crack susceptibility of microalloyed steels during continuous casting. And then the last will be Farnoosh. She will be talking about implementation of quenching and partitioning methodology in different industrial processes. So for the first part, I will introduce about additive manufacturing and the selective laser melting, the method that we use to sinter steels, duplex steels, and martensitic stainless steels. And then I will discuss about the microstructure hierarchies and heterogeneities in SLM fabricated stainless steels. And then I will go through the experiments that we conducted at room temperature and high temperature in Gleeble on determining the properties at low, intermediate, and high temperatures. So as an introduction, AM is a process of building 3D objects and from a CAD/CAM files in layer by layer panel. There are different types of AMs: solid based, liquid based, powdered based. And we will work on powder based AM, and I will present on selective laser melting and compare it with in some cases with electron beam melting. So selective laser melting is a rapid prototyping technique that fuses and solidifies powder materials with an aid of a focused laser beam, as you can see in the figure, where we have this a powder bed, and then we can build the component by scanning laser layer by layer and consolidating the materials. And there are certain advantages associated with this. The technique that, like the production of complex shapes, can be done. It's a very fast heat transfer, so we can get interesting microstructures. We can produce functional gradient materials, and we can design and tailor the microstructure and properties. Some disadvantages of SLM are high residual and internal stresses, low build volume, optimization is a challenge, and the equipment is expensive. We have a lot of applications in automotive, aerospace, biomedical, military, fashion, and jewelry. So here are the 3 steels that we used selective laser melting to produce components, and we used austenitic 316L, duplex 2507, and martensitic 420. And on the right side here, you can see the microstructure after the selective laser melting, and duplex stainless steels and chromium cobalt molybdenum alloy. How the microstructure looks like after SLM. So I will go a little bit deeper in this microstructure, and here you can see a scan. And if we go further within this scan, we see bigger grains. And if we go further in these large grains, we see subgrains of very small size that are around 500 nanometer. So it is a hierarchical microstructure which has laser scans, and then grains, and then subgrains. And here is the microstructure of martensitic 420 SLM, and you can see the similar kind of microstructure, hierarchical microstructure, is obtained. And you can also see the martensite needles there in the SLM built sample. So here I will say that it is a hierarchical structure. If we look closely, we have bigger grains and we have subgrains inside. The subgrains can be of also different sizes that you can see into adjacent grains. They have different sizes. And within these subgrains, if we look at the grain boundaries, we can find the segregation of certain elements and also some oxides. So it's a hierarchical microstructure and heterogeneous microstructure, which open up the possibilities to achieve properties that we cannot get in a conventional cast or produced steels. So now I will discuss about the mechanical properties of these SLM316 steels at room temperature. So this is as a built sample, tested in a tensile test. And in this case, we can get a yield strength of 240 to 300 megapascal, tensile strength of 500 to 600 megapascal, and a elongation of 40 to 45%. This is the typical properties of austenitic stainless steel with a hardness of 140 to 180. And if we compare these properties with SLM built, which is a hierarchical and heterogeneous microstructure, we can see we have a better yield strength, that higher tensile strength, similar elongation, and higher hardness. So for now, I can say we can get a clue that this hierarchical microstructure is different. Chemical composition is the same, so that is contributing towards superior mechanical properties at room temperature. So this is this is the characteristic microstructure, and after deformation, we can actually look through the microscope that how this material is deformed, how the substructure dislocation loops are produced, and how this oxides that are contributing towards the high mechanical strength of this material. So this is the second duplex steels, 2507, and this is the as-built sample. And interestingly, after SLM, it is only ferritic instead of duplex. And as produced, we get a tensile strength of 1321, megapascal, yield strength 1214, and hardness of 450, which is comparatively very high to duplex stainless steels and also ferritic stainless steel. And then, since it's only ferritic, we try to do the heat treatment to get the duplex structure. And after the heat treatment, we found out that the mechanical properties reduced, the mechanical strength reduced to 920, and the elongation reduced drastically to only 1.8%. So then we looked in the microstructure and tried to understand why this happens. And then we found out that although there is a phase transformation from ferrite to austenite, we get the duplex structure, but at the same time, we precipitate intermetallic phases like sigma and three phases. So that is responsible for the low elongation in these states. So for the room temperature application, with such a structure, heat-treated structure, we don't get promising properties. But we will see that these precipitates actually contribute towards high temperature mechanical stability in the steels, which I will show later. So this is the third steel that we built, the mechanical properties of SLM420, that is a martensitic steel. And you can see the SLM structure, that is a hierarchical structure, gives us very, very high promising properties, that the 1800 megapascal is a strength. And if we compared it with the annealed cold drawn 420, then the 800 megapascal is the tensile strength. Elongation is slightly low, but it is comparable with the annealed sample. So now I will show you if we increase the temperature from room temperature to 250 degrees centigrade, how this hierarchical structure contribute towards the high temperature mechanical stability. So at 250 centigrade, you can see the SLM samples. They show superior properties, high mechanical strength, but still they also keep the hierarchical structure, the heterogeneities in the SLM as built sample. So we still find the structure in stable at 250 degrees centigrade, and we get very high properties compared to EBM and conventional steels. And then we did the mechanical test at 800 degrees centigrade, and at 800 degrees centigrade is a quite high temperature for steels, and we observe the stress relieving grain recrystallization, grain growth in conventional steels. Whereas in this case, if we look, there's a lot of strain hardening happening, and we are getting very high mechanical strength of 400 megapascal. And the microstructure shows that the hierarchical structure is not changed or modified even at 800 degrees centigrade. So suggesting that this microstructure, which is a heterogeneous microstructure, is contributing even at 800 degrees centigrade towards the mechanical stability of the steel. Then we were starting thinking like, how stable is this microstructure? So first thing I would like to say that this hierarchical microstructure is developed, the subgrains are formed due to the segregation of certain alloying elements at the grain boundaries. So they make cells. And to break down those cells, we need to diffuse those alloying elements from the grain boundaries or subgrain boundaries. So then we started heat treating them at different temperatures for different times and trying to understand why and how long this microstructure is stable. So we heat treated at 1100 degrees centigrade and 1200 degrees centigrade and investigated the mechanical properties as well. And as you can see, we have proposed the mechanism that these subgrains, when they are heated up to 1100, they start merging together above 1000 degrees centigrade, and 1100 it becomes obvious. And at 1200 degrees centigrade, then we cannot see any subgrain microstructure there. So it requires quite high temperature to change or destroy the microstructure that we get in as-built SLM 316 stainless steels. So based on the mechanism, that then we can understand if the grains are not coarsening, the structure is very stable, then it's leading to superior properties of these steels at high temperature. Then the mechanical properties of SLM duplex stainless steel at 1200. So at room temperature, we got good strength. After heat treatment, we got segment-free precipitates that led to poor elongation. But in this case, when we had heat treated and without sigma precipitates, we were able to get 200 megapascal with 30% elongation, and we didn't have a sigma precipitates. Then we did the same heat treatment and tried to introduce the sigma precipitates, and then we conducted the mechanical test. And then we found out very interesting results that the sigma and he precipitates actually contribute towards high temperature mechanical strength. So we got almost double mechanical strength, 400 megapascal with sigma precipitates as compared to 200 megapascal with no sigma precipitates. 25% elongation, and the mode of failure was tactile. So these are the XRD pattern of these two different samples without sigma precipitates and with sigma precipitates. So we were able to say like that duplex stainless steel with sigma and Chi phases in the microstructure around 16 weight per sigma content can actually give better mechanical properties at high temperature, as high as 1200 degrees centigrade. So then I will introduce the latest work that we are conducting here, is that we are producing high entropy alloys that can be possible candidates for high temperature applications in very harsh environments. For instance, this alloy, tungsten, tantalum, titanium, vanadium, and chromium. This is basically, we designed it for plasma facing materials, and we want to investigate the stability of the structure and high temperature properties of these materials. So they are designed on base of the high entropy concept. So we did the spark plasma sintering to consolidate these materials. So they were consolidated, and you can see that when we have elemental powders, we can get almost signal from the alloying elements like tungsten, titanium, tantalum, vanadium, and chromium. And after consolidation, we get a single solid solution. This means we have made up an alloy of this high entropy alloy. And this is the microstructure that and you can see the microstructure is has a contrast, and we get some titanium carbide particles, but the rest is quite homogeneous. And you can see the elements like tungsten, tantalum, chromium, vanadium, and titanium are homogeneously distributed in the solid solution. Then to investigate again the high temperature properties, we started at 1000 degrees centigrade and 1200 and 1400 degrees centigrade. And we performed this test, and we got very, very, very good mechanical properties for this material. So that it means it can be used for very high demanding applications up to 1400 degrees centigrade. So these are the fracture surfaces that we got. Different mechanisms were operative at 1000, 1200, and 1400 degrees centigrade. And then we check the high temperature stability by doing the heat treatment, heating and cooling down up till 1400. And then we did the XRD, and we found that the structure that we form in this high entropy alloy is very stable, and it doesn't, no secondary phase or precipitates appear during the heat treatment up till 1400 degrees centigrade. So same BCC structure up till 1400, no precipitation and very high mechanical properties. So these are the no chemical composition change, a little bit oxides form in this. So this is a comparison to state-of-the-art alloys, and you can see the existing materials and our high entropy alloy at room temperature, excellent yield strength. At 1000, better than the existing from the literature. At 1200, also much better, and at 1400. So this way we can design materials and investigate, tailor their microstructure, and investigate their high temperature mechanical properties and the thermal stability, and also can use the heat treatment process to tailor a microstructure and the properties. So these are the articles that we have published that you can read to get more information if you are interested. Okay. So these are the acknowledgements of the funding agencies, and I will now give the presentation to Rusa. Yes, Rosa.
Yeah, hello everyone. My name is Rosa Pineda Huitron, and I'm a PhD candidate at Luleå University of Technology. Before starting the presentation, I would like to thank to the Gleeble staff for organizing and giving us the opportunity to be a part of this Gleeble webinar series. It is a pleasure for me to share with you a part of my research that is focused on the study of crack susceptibility of microalloy steels during continuous casting process. This project is carried out in collaboration with SVEDIM and SAB. For the people that is not so familiar with the process, so continuous casting is a metallurgical process that was introduced in 1940s, 1950s, more or less, and it is actually was introduced to try to replace the ingot casting to improve productivity. So nowadays, continuous casting is considered the most efficient and the cost-effective metallurgical process for producing large volumes of steels into semi-finished shapes. So the production of steels by continuous casting, it covers around 95% of the world's production. So it is like a quite important process around the world. There are different types of casters, but today I will be focusing bending caster. So then there are different segments that we must consider just before going through the methodology. So in this case, going from the top to the bottom, there are actually different segments that are the key during continuous casting. Starting from the mold. Actually, the mold is where the material starts its first solidification. The mold is also named as a primary cooling. And just below the mold, there is the rest of the segments are also identified as secondary cooling. In this case, the material continues solidifying here by the help of water flow that is provided by different nozzles that are located in between the support rolls. Keep in mind these two sections, bender and straightening, because from there, all this project or all this research started. One of the critical issues during continuous casting, especially for microalloy steels, in this case, high-strain alloy steels, is the presence of transverse corner cracks. Transverse corner cracks are actually detrimental for the process because those affect directly the productivity, yield, energy, and of course have a great impact in economy. So this type of cracks appears as a light shape, and those can actually reach up to 3 centimeters length and have up to 5 millimeter depth. So then it is quite like a very big topic and very common also, but complex to understand for many steel companies around the world. Our main approach is to try to combine different features in this work in order to understand the formation of transverse corner cracks, starting from the chemical composition of the material. And we know that the chemical composition of any material is the key to understand the material's performance. So the chemical composition together with the process parameters, these will give us actually the important answers, let's say, regarding the microstructure evolution during, or the mechanisms during crack formation. So the thing that we did here is like we identified 2 main zones that might be risky for the cracking formation during continuous casting, which is the bender and the straightener. As its name says, it's like bending. It requires like the formation of the material. The temperatures here are oscillating around 1,200 degrees. So then here, the material is subjected to a combination of compressive and tensile stresses. In the straightening, which is also considered a high risk section or zone during continuous casting, is because the material here is almost completely solidified. So the temperatures here are going down, and then it's also like, again, a combination of tensile stresses and compressive stresses. Knowing that tensile stresses are needed actually for creating cracks in the material. So what we did is important to mention just before the experimental part. So these temperatures that you can see here are the actual temperatures that were possible to measure by installing pyrometers in the caster. So then by taking these parameters together with the casting speed in the process, it was possible to try to simulate the process as close as possible to the reality in solid state by Gleeble system. So we were using actually this type of specimens with a diameter of 6 millimeter and gauge length of 12 millimeters. The thermal cycles looks like this. So then we were actually controlling the heating of the specimens at 20 degrees per second just before austenitization at 1300 degrees. We applied a holding time of 5 minutes. And the idea for this was to ensure that not just the austenite could be homogeneous, but also like to actually make all the precipitates to dissolve, so those cannot affect the final results during the test. So then in this case, we were performing this static tensile test at different temperatures, which covers more or less the temperatures that we saw previously. So tensile test was performed from 600 degrees up to 1000 with 100 degrees in between every temperature as a step. We were also applying 3 different strain rates as trying to simulate more or less the effect of the casting speed, taking into account that the lowest strain rate here, it replicates the real casting speed that is applied in the real process. Yeah, so then how we determine after getting, after obtaining the results from the thermomechanical test, so we were applying actually different numerical criteria. So then to determine actually the crack susceptibility, in this case, well, as you can see here in this table, so the first equation are just to plot the flow curves that actually are very well known, the stress strain, the engineering and the true. But for the crack susceptibility determination, we were using the combination of 3 different criteria. The well-known reduction of the area, that actually we believe that this is the most common, but also it can overestimate some of the results. That's why we were combining these other 2, the true fracture strength ductility and also the true total energy. It is important to mention that the true fracture strength ductility, it is actually valid after the necking, while these just 2 models are just valid upon the onset of the necking. So then this criteria was actually considered new for determining the crack susceptibility, that in a combination that can give more accurate results. The crack susceptibility, the results looks like this. So then by comparing the reduction of the area method together with the true fracture strength ductility and the true total energy, we could obtain this type of results. Maybe this can be a bit confusing now, but I will help you just to highlight that there is a range of temperature that we can see something is happening in the material. So starting from the reduction of the area, so there is a point that the material is really like, we can see that it's changing, the ductility is dropping. So then that we can see here is that the true fracture strength is as well, since this is based on the reduction of the area as well, but it's taken in consideration the true stress and the true strain at the fracture point. So then we can also see how the material is like reducing the ductility, and the same in the true total energy. So then we can say here that the lower the strain rate, the lower the ductility. So the effect of the strain rate is also playing an important role here. And then the crack susceptibility can be said like it is in between the 700 and 800 degrees and less susceptible to at 900, 1000 degrees. What is happening here normally is that this is mainly related with the recrystallization of the steel. The fractography and the microstructural analysis is telling us that we had an important findings here, that we have a combination actually in the left side of the ductile and brittle behavior in the material. So this was found an intergranular fracture. But also we believe that the presence of the inclusions are also affecting the behavior of the material. So we have the microbone nucleation and coalescence of large inclusions. In the right side, in the microstructural analysis, so we actually saw that there is like a combination of different phases. We saw also that we have normally ferrite and ferritic and perlitic structure, but within ferrite structures, we found that a combination of allotromorphic ferrite, acicular ferrite, and Widmanstatten ferrite. So of course, it is quite difficult to see it here, but this thing is like, according to the literature, so Widmanstatten ferrite is considered detrimental. Widmanstatten ferrite is actually a phase that grows in parallel plates in a preferential direction in the austenite previous grain, or it can also grow from allotromorphic ferrite. But this actually, it has been demonstrated that it results in cleavage cracks of the material. These plates works during deformation, the dynamic deformation, as a preferential site for cracking formation to occur. So this phase was considered one of the reasons why the material is susceptible for cracking formation. Further analysis, it was done by using an open source script in MATLAB that could actually is based on the Hall page number, and then this could actually give us the or approximate the austenite grain size in non-homogeneous structures. So then we measured the previous austenite grain size in the material and the volume weight average grain size. I'm not going through this in detail of how I calculated, but I will give you the link later on in case you are interested in the methodology and the numerical approach in this research. It is also why I measured the previous austenite grain size. It's because previous studies have been demonstrated also that Widmanstatten ferrite can grow or can be promoted actually if the previous austenite grain size is large, is promoted by the deformation and is promoted also by the grain size of austenite. So what we concluded in this work is that these three criterion is like giving us more or less where the material is susceptible for cracking formation, that is between 700 and 800 degrees, and less susceptible at 900 degrees. So the effect of the strain rate actually plays also an important role, as I mentioned before. The lower the strain rate, the lower the ductility. So then if the company decides to increase the casting speed, it will be beneficial for the material as well. The fracture of the steel occurs with a combination of dural brittle and quasi-cleavage and intergranular fracture mechanisms. This can be also promoted by the formation of impurities, microvoids, or that can also be promoted by during plastic deformation. Microstructural analysis also confirmed that the crack susceptibility of the steel is associated directly with the Widmanstatten ferrite transformation occurring at high temperatures. Actually, one of the conclusions that could help the company, it was to, by avoiding this ductility range, or low ductility zone, as I call it, it is possible to avoid the risk or avoid, the formation of cracks, transmechanical cracks in the material. Plants also the company also performed some plant trials, and it was also possible to see that this could be beneficial for them. I will leave you here a link in case you are more interested in reading further this paper. Thank you very much for your attention, and I will give the floor to my colleague Fanush Rosa.
Okay, thank you, Rosa. So, Yes, my name is Farnush Ferzan, and I'm Associate Senior Lecturer at Engineering Materials subject of Luleå University of Technology. The work that I present today is briefly describe what I have done during my PhD thesis. And I would like just to explain a little bit about the ideas that we worked on, but I will not go through the detailed results that much. And you are very welcome to contact me if you have any further questions. The title of my presentation is Implementation of Quenching and Partitioning Methodology in Different Industrial Processes, such as laser welding, bearing steels, and hot stamping. So, as you may already familiar with this diagram, the banana graph, it shows a tensile strength over elongation, and you can see that there are different groups which are in the category of advanced high strength steel, which means that they have over 600 megapascal strength. The first generation is the ones which have very high strength but low elongation usually, and the second generation are the ones which have both good strength and elongation, but the problem is that they are highly alloyed, so they are expensive and it's not possible to use them in many of the applications. But the current focus of the research is on the third generation of advanced high strength steel, and among them there is quenching and partitioning steels, which was the main interest of my work. So let me explain what is quenching and partitioning process. We should first austenize the sample fully or partially, and then we will quench the sample to a temperature below MS but still above MF. So it means that the sample will partially change to martensite. The structure will be martensite and austenite after this stage. And then in the second stage we have isothermal heating, which could be the same temperature as quenching temperature or higher temperature. And during this partitioning stage, carbon will partition out of martensite to austenite. As a result, we have tempered martensite, which is not as brittle as before, and we have higher carbon content in austenite, which helps us to stabilize austenite at room temperature and give us higher ductility. And then at the end, the last stage is the final quenching, which could result in some fresh martensites in the areas that we have not enough carbon content. Depending on the chemical composition and the time and temperature of partitioning, it's possible that we get other phases like bainite or other ferritic structures. But normally QP steels contain over 1.5 weight% silicon to inhibit carbide precipitation, because carbides consume this carbon and then it's a lower chance to stabilize austenite. In addition, most of the QP steels are designed to have manganese, nickel, and chromium to retard ferritic, and bainitic transformation and to increase the austenite stability. So if we look at the objectives of our work, we have 3 processes. The first one is welding. In this work, I worked on laser welding. You know that laser welding has a very high concentrated energy, and then it means that after welding, we will get martensite because of very high cooling rate. And this martensite is not what we would like. So the idea of this work is coming from quenching and partitioning, and what we have done is that we controlled the temperature just after welding in a special quenching temperature between MS and MF. So we have some martensite, and after that we increase the temperature by heating the sample again, but for a very, very short time. Depending on chemical composition, it could be just a few seconds or maximum a few minutes. So at the end, we already tempered the martensite, which is formed during the first quenching, and we have some stabilized austenite. So that's very interesting, because we normally need to do post-welding heat treatment after laser welding, and depending on chemical composition, it could take between like 5 to 30 minutes. The second application was the bearing steels. You may know that bearing steels are usually high carbon content steels. They should be hard and usually martensitic. So that's the thing, but we normally don't like to have high carbon martensite because, as you know, it's as brittle as glass. So the ductility of such structures is like 1%, for example, in the bearing steel, like 100 chromium 6. What they usually do for bearing steels in industry is that they quench first and then temper for 1 or 2 times for 1 to 2 hours. The other method to produce bearing steels, which is new, is austempering, and which will result in carbide-free benedict steel. This kind of structure is really good. It could have very high toughness and very good strength at the same time. So that's really good. But the point is that it takes several hours, or we can say several days. So that's difficult to produce such structure because it's costly and time consuming. But the idea of this work was to design the chemical composition in a good way that we could use quenching and partitioning for just a few minutes. And we have tested this. And the last one is press hardening. As you can see in this picture, you can see that let's see. Just I'm just lazy. Oh, sorry. Yes. Sorry, yeah. So as you can see here, after austenitization in normal hot stamping, we have the hot forming between 800 to 700 degrees C. But then the sample will suddenly, let's say, it will quench. So what we have is that we have a martensitic structure, which is not good most of the cases. But then if we combine quenching and partitioning with hot stamping, you can see this. It means that after hot forming, we can quench in a die quench, which is set in a specific temperature that we want as TQ, and then we can take the sample out of the die quench to the second furnace. And in the second furnace, we can apply the higher temperature of partitioning, and then final cooling. The objective of all these three is to shortening the ordinary processing time, development of quenching and partitioning in service to industry, and designing the process by understanding the microstructural evolution. Just very shortly, we can take a look at the results. In the first application of welding, we selected 3 quenching temperature, 3 partitioning temperature, and 3 partitioning times. So 27 different conditions. All the samples were treated in Gleeble, and based on the microstructure and the hardness results, we selected a few of them to test by real laser welding and using induction heater to apply the heat after quenching, so in the partitioning stage. And during this time, 2 thermocouples were welded 1.5 millimeter far from the fusion zone to control the temperature, because the most critical area for the failure of the welds is in coarse grain heat affected zone. So we want to control that area and have the best results in that. Here you can see the tensile test results out of the laser welding and quenching and partitioning afterwards in different conditions. You can see that all of them have higher strength than base metal, and in some of them we have the same ductility or even higher. And for example, you can see that at 450 that the partitioning temperature was not high enough, so it's almost the same as a reference weld, just as welded, and quench and tempered condition. But what is important, and we saw, is that is there any grain growth? And you know that the structure is martensitic, so it's not possible to do like normal measurement of the grain. So we need to do EBSD and measure the packet size of martensite. But what was very interesting was that at 640, we saw a very huge grains, which are approximately nine times bigger than what we saw in 540. So here you can see the grains which are inside this margin, and these huge grains can decrease the toughness very much. So the best condition that we found was at 540. And if you want to take a look more at the results of this work, I invite you to take a look at these 2 papers. They are the main papers out of this publication, and some other smaller works based on that. Currently, I'm working on MIG-MAG welding with the same idea of quenching and partitioning. That work is much more complicated because we have filler metal in that, but in this case, with laser welding, we don't have filler metal, so it's a bit easier. The second application about the bearing steel, we also used quite a high carbon steel, 0.6 with 1.6% silicon, and tested different conditions. We used both Gleeble and furnace +2 salt bases to prepare the samples and compare the results. Here you can see the microstructure. I think this this picture could show you the austenites around the martensite, which are stabilized during partitioning very well. And it's the same out of the color etching by optical microscopy, where you can see austenite in white and tempered martensite in blue. Results are really interesting. We have tested all the samples in Gleeble at room temperature. You can see what we have done. First, the samples were like A, and heat treated at in Gleeble, taking out the samples, polished the critical area to avoid any rust or scratches, and then tensile test. And we saw that samples quenched at 25 degrees C have over 2.4 gigapascal strength and 4 to 5% elongation, which is really good. The results of this could be found in 2 other papers. I invite you to take a look, especially in the first one. You can find the control maps to design all different conditions. If you want different, let's say, strengths or ductility or toughness, you can find everything in that paper. this one. And the last one, which is ongoing project, is about the hot stamping. We have used the settings which are used in Gestamp. This is a hot stamping company in Luleå, and we have a good collaboration with them in this project. You can see that we have used a very tiny sample first in Gleeble. The sample size is 4 mm in diameter and 6 mm in height. So they are cut from a 6 mm sheet. And then you can see the gas nozzles, which we have used them for cooling to a quenching temperature. This work has different difficulties during using Gleeble, and then thanks to Gleeble staff, then we figure out how to simulate the hot stamping process. The results of this project is not published yet, but this is from the previous work by my supervisor Esa Vurinen during a ductoform project a few years ago, and it showed that quenching and partitioning could improve the ductility around 2 times comparing to the boron steel, which is using for this application. And I would like to thank you everybody for listening to this presentation, and give back to Farid.
Great. Well, thank you. This is Dan. I want to thank our presenters for a lot of great information and different types of information, different types of studies. So this was great. We do have a few minutes for questions. Maybe Farnoosh, if I can start with you, since you're, I think, already near the microphone. A question for you was, it says early in the presentation, I talked about the Q and P method. Is that already used in industrial mass production, or is that still in the research phases?
Quenching and partitioning steels are produced already. We use the steel from SSAB in Borlänge, Sweden, but it's under development in the companies as well. But the ideas that we have applied after welding or hot stamping is just under research. So I don't think it's produced by industry yet, but we are also in very close collaboration with industry, and I know that there are many companies who are interested and started working on that. Especially hot stamping is started from, I can say, 10 years ago.
Great, thank you. Rosa Maria, a question for you. The question was, have you tried to perform experiments by melting the specimen? So sort of a melting, potentially, and hardening as well, solidification.
Yeah.
Well.
Actually, there is a new project that is ongoing now. We already perform in situ melting experiments to try to apply more parameters into this problem. And actually, there is a coming manuscript with that analysis. So then, yeah, I have been doing that and trying to approach as close as possible, you know, the situation that the material is subjected to into the casting, into the laboratory scale. Of course, with some limitations, but we are trying to understand the cracking mechanisms.
Very good, thank you. And Dr. Akhtar, a couple of questions for you. One question was, if you could maybe talk a little bit about the industrial applications of SLM 316. Where is that currently being used or planned to be used?
It is in plan to be used, and we have several companies in Sweden, including aerospace companies. They are working on the development of steel components for real applications.
Okay, and one of your slides, and I don't know which one, I apologize. The question was, how does the SLM produce the columnar structure in austenitic steels? So I think there was a slide where you showed that columnar structure, and we're wondering how that occurred.
The microstructure in SLM is actually cellular solidification that is happening, because it's very, very fast cooling as well. So it's not like a very fast growth, but the columnar, the solidification is cellular solidification. That's why we're getting this kind of special microstructure in SLM steels.
Okay. And then maybe one more question here, we're running out of time. The SLM 316 shows higher mechanical properties as compared to the conventional 316. Have you investigated the differences in fracture toughness properties?
No, we didn't test the difference in the fracture toughness.
Okay.
But it's a good idea actually to investigate the energy for fracture for both different microstructures. Yes.
Okay, great. So we're about out of time here. I do want to, again, thank you and your team for a great presentation or great presentations. These were really interesting. It was nice to see different materials, different applications. So appreciate the time you spent putting the presentations together.
And thank you also for organizing this and giving us the opportunity.
Great. If anybody, if there are more questions, if you would like to reach out to the team at Luleå, please, you can reach out to me. I think everyone has my email address. It's dan.quigley@gleeble.com, and I can make that connection for offline discussions. If anybody has a question about how Gleeble can support your research, please email me, and I'll be sure to connect you with an application expert in your region or in the application that you're interested in. Again, I hope everyone stays safe and healthy, and thank you for joining us and spending some time with us today. Have a great day.
Thank you.
Thank you.
You too. Thanks.